Hello, good evening students. So today our topic is saturation curve or magnetization or BH curve. So already we have discussed that the materials have been classified into three types: ferro, para and dia. Right? So let us discuss the saturation curve or the magnetization curve for. Okay. So this saturation curve will be drawn between the magnetic flux density and the magnetic field intensity, B versus H. So we need to observe the characteristics between flux density and field intensity. So the curve is said to be magnetization curve or the saturation curve. Okay, so actually what happens? So simply consider a settler coil and apply a DC source, DC EMF, connect 1 ammeter. Okay, so whenever you apply a DC source, some amount of current will flow through the coil. That amount will depends upon how much voltage you are applying. So already we know that any coil which carries a current should act as an electromagnet which develops the fluxes. Right? So initially when you are not pumping any current through the coil, so there is no magnetic flux density and there is no magnetic field intensity. Magnetic field intensity is nothing but it's like a MMF force, magnetizing force. Right? So both are zero. So initially it may start from the origin 0. So when you pump a small amount of the current, when you start pumping current through a coil, then obviously flux density and the field intensity both will be increases rapidly up to a certain amount of the current. Here that point is up to a knee point. As per the graph, if you observe from origin to knee point, there is a variation for B as well as for H, rapid variation for flux density as well as field intensity. Flux density unit is Tesla, field intensity unit is ampere turns per meter. Okay, so once it has been reached the knee point, then if you observe at the knee point, there may be a slight variation for flux density as well as the field intensity. So at knee point, if you observe at the end of the knee point, if you observe, if you will increase the field strength, magnetic field strength or the field intensity H value, then there is no change in the magnetic flux density. That portion is said to be saturation. So if you observe the graph, flux density versus field intensity consisting of three portions: unsaturation, knee point and the saturation. So under the unsaturation portion, there may be a rapid variation, rapid increment for B as well as H. But in the knee portion that lies in between unsaturation and saturation, there exists a portion which may be called as a knee. So under this portion, there may be a slight variation. There may be a slight increment for flux density as well as the field intensity. Once it has been reached maximum values, flux density as well as your field intensity both reaches the maximum. Even if you increase the magnet strength or magnetizing force, then means even if you increase the more, if you are pumping more amount of the current, once it has been reached the knee point, even if you pump the more amount of the current through a coil, then there is no change in the flux density. There is no change in the flux density, which is nothing but a saturation portion, which is nothing but a saturation. Clear? Next slide. So here the terms which we have discussed as per the graph. So what is the first term? Magnetic saturation. So limit beyond which magnetic flux density in magnetic area does not increase sharply further with increase of MMF. Clear? So even though if you increase the magnetizing force, magnetic field intensity, which is nothing but capital H, there is no change in the flux density. So that portion is said to be magnetic saturation. So what about the residual magnetism? It is the amount of the magnetism left behind after removing the external magnetic field from the circuit. Clear? Means even though if you are not applying any magnetizing force, capital H is 0, then also some magnetism will be present. Capital B will be exist small amount. Capital B will be exist in a small amount. Then that property is nothing but that mechanism that we are pronouncing as a residual magnetism, or else it may be called as a retentivity of the material. Flux density retained by the magnetic material is called a residual magnetism, even though if you are not applying any magnetizing force. So what about the residual flux density? Same. When H is equals to 0, then the flux density will be available, remains in the magnetic material or the magnetic circuit. So which is nothing but your residual flux density. Right? So this is your magnetizing curve. B versus H generally we will draw. In the same way, B you may convert in terms of flux. So flux versus force you can apply, right? Ampere turns, magnetizing force. So generally the BH curves will be for different materials. If suppose you have been taken sheet steel, then BH values may be the higher. So what about the cast steel? Somewhat reduced. Cast iron, it's maybe a linear. So already if you observe the figure, so where the curve shows the flat ends, it may be saturation region, right? Where the flux changes rapidly, unsaturated region. The transition region between the unsaturated and the saturated is a knee point. So generally the relative permeability, the magnetic material consisting of a relative permeability which depends upon the value of the flux density, right? B is equals to mu H. So relative permeability will depends upon the magnetic flux density, but for the non-magnetic materials it is always constant. For the air gap is also a constant. That value is 4 pi into 10 to the power of minus 7 Henry per meter. So general our intention is we need to discuss about the hysteresis and eddy current losses. We need to discuss about the hysteresis and eddy current losses. Okay. So for the hysteresis we need to focus on this diagram. Okay, we have taken a coil, right, and we are pumping, we are applying a source, voltage source, okay, and we have been connected a ammeter to measure how much current flowing through a coil. If you observe here, changeover switch will be there, reversible switch. Okay, so just assume that whenever the switch is at one terminal, maybe forward direction you are pumping the current. If suppose the switch position at 2, in the reverse direction you are pumping the current, means you are changing the direction of current through the coil, and it is our variable resistance. Okay, so initially, actually we know that, right? So what is a saturation curve or the magnetization curve? The draft between the B versus H, the draft between the B and H, right? So always the flux density we need to consider on y-axis and magnetic field intensity H on the x-axis. So B versus H we need to draw. So initially the curve will start from the origin O point. If you observe the graph, initially the curve between the B and H will start from the origin, because if you are not pumping any current through a coil, there is no flux density and the magnetizing force, both are 0. So that's why the curve will start from the origin. So whenever you start pumping a current through a coil, okay, and slowly you are increasing the current, pumping current through a coil, then there is a increment in both the parameters, that is flux density and the magnetic field intensity, both will increase rapidly, and they may reach up to a maximum point, that is A, up to the maximum value A. Then after A, what happens? Even though if you will pump more huge amount of the current, after reaches the point A, then there is no change in the B. It may be a constant, that is saturation position. Okay, so up from 0 to A, there is a huge increment between of flux density as well as the magnetizing force or the field intensity H, right? So after A, what happened? What I am doing, I am slowly decreasing. If you will increase, there is no use, right? There is a saturation. So that's why what I am doing, slowly I am decreasing the current value. So when you are decreasing the current value, then the values of your B and H will start decrease. The values of B and H, they will start decreasing. At certain point B, the H will become 0. At point B, H will become 0. But even though the magnetizing force is 0, but there exists magnetic flux density. Right? Even though you are not applying any magnetizing force, then also magnetic flux density will be existing, so which is nothing but residual magnetism. So in the graph, the OB portion will give the residual voltage or the residual magnetism or the residual flux density, BR. OB portion will indicate the residual flux density, residual flux density, residual flux density. Clear? So this is the explanation regarding that. So just go through the first point. When current is 0, your curve will start from the origin. When current is increased from 0 value to some certain value, then H and B both are increases. That shows O to A line. Next, so at point A, P and H will reach as the maximum. So no change in the flux density, even though if you will increase the current value. So here, when the current is decreased, then H is decreased along with the direction of B, but it doesn't follow the same path, right? O to A. If you observe, O to A is increment path and A to B is the decrement path. Why both the paths are different means due to the residual magnetism, right? Because the residual flux or the residual flux density may vary from time to time. So that's why they may not follow the same path. Okay, so O to B is the residual flux. So if you observe the sixth point, if the direction of the current is reversed, the direction of H also gets reversed. The increment in the H in the reverse direction following the path B to C. So just you observe here. So once you reaches the point B, then what I am doing, I am switching the reverse direction. Means at point 2 I am going to switch. Means you are pumping current in the reverse direction compared to previous. So what happened at that time, the magnetizing field intensity or the magnetizing force starts increasing, but in the reverse direction. Initially you have been applied at terminal 1, now you are applying at terminal 2. So magnetizing field strength or the magnetizing force is going to be increased in the reverse direction. So what about the magnetic flux density? It goes on decreasing. Okay, so the B to C portion will shows that the magnetizing field strength may be increased H value, but in the negative direction, that will shows minus X axis. But coming to the B, it will reach as the minimum position, that may be 0. Right? It's not 0. It starts on decreasing. Okay, it's the B value maybe starts on decreasing. So if you observe at point C, the value of H will become as negative. At point C, the value of H is negative. So which is known as a coercive force. So from the point C again up to D, when you are going to increase the current in the reverse direction, then what happens? It may be reaches up to a maximum value. Like in the forward direction, it may reaches the maximum value at point A. In the same way, in the negative direction, it may reaches the point D. Now if you start decreasing the current in the same reverse direction, so what happens? From the D, it may take another path because the residual flux may vary. So it may goes up to D to E, again it will E to F, again it will be F to A. So in this way, we are forming a hysteresis loop. A loop which is nothing but a hysteresis loop. In this way, we are getting a loop. In forward direction, A, B, C, D. In the reverse, A, B, C. Okay. O, A, B. Right. OAB, next BCD, DEFA. So in this way we are getting a loop which is nothing but hysteresis loop. Hysteresis loop. So whenever the negative value of H is, which is called as a coercive force, H is increased more in the negative direction, B gets reverse. At point D, again magnetic saturation takes place but in opposite direction. So at point D, B and H get maximum values, right? If we decrease the value of H in this direction, again B decreases following the path DE. H gets 0 valued but B with the finite value, right? Same, everything will be the same. At last we will get a one hysteresis loop A B C D E F A. Clear? So actually what is the hysteresis? The phenomenon of flux density lagging behind the magnetizing force. So if you observe the graph, okay, at point B, right, at point B, H will be 0. At point B, H will be 0, but some magnetic flux density is existing, right, B to C. So B is lagging behind H. B is lagging behind H. B is lagging H. Okay, B takes the position behind the H. So that's why what we are saying in hysteresis is a draft between the B and H, and always B lags behind the magnetizing force H, which is known as a magnetic hysteresis. So what about the coercive force? Already we have just now I have defined, right? The negative value of the magnetizing force that reduces the residual flux density of a material to 0. That reduces the residual flux density of a material to 0. Clear? So it is nothing but your coercive force. So what about the retentivity? Degree to which a magnetic material gains in magnetism after magnetizing force reduced to 0, means even H is 0, there exists a magnetism in a magnetic material which is nothing but a retentivity. Some flux may be available. Those fluxes are residual flux and the property is said to be retentivity property. So the hysteresis losses in an iron core is the energy required to accomplish the reorientation of the domains during the each cycle of the alternating current applied to the core. If you apply AC supply, alternating supply for the core, then what happens? Forward direction first. So orientation of the domains. So maybe change in the forward, in the negative. So for every cycle we need to go for the magnetization, demagnetation means positive cycle, negative cycle, positive cycle, negative cycle. So we need to reorient for every cycle. So in that process some energy is going to be wasted. So that loss is said to be hysteresis loss. So the area enclosed in the hysteresis loop formed by applying an alternating current to the core is directly proportional to the energy loss. So actually how to define the hysteresis loss? The work done by the magnetizing force against the internal friction of the molecules of the magnet. For the positive half cycle, orientation of the molecules, and for the negative half cycle, orientation of the molecules will be different. So we need to adjust them in unidirectional, right? So for every cycle, magnetization and demagnetization. So in that process, whatever the energy we are using, that may be wasted in the form of heat. So which is said to be hysteresis losses. So it is known by pH, and which is given by eta Bmax power 1.6 into FV watts. Loss is measured in terms of power, so that's why unit of the loss is watts. So pH is hysteresis loss in watts. So what about eta hysteresis or the Siemens constant measured in joules per meter cube, and Bmax flux density Webers per meter square or Tesla, frequency F number of cycles per second, and V volume of the material per meter cube. It may be measured per meter cube. Volume unit is meter cube. So by using this formula we can measure the hysteresis loss. So the hysteresis loss or the hysteresis loop may vary for two different materials. That is, first one is soft magnetic material and second one is hard magnetic materials. So for the soft magnetic materials like iron, silicon, steel, so the hysteresis loop may be, it may dissipate small amount of the energy, and it consisting of narrow magnetic hysteresis loop. If you observe the graph, it consisting of narrow magnetic hysteresis loop, and it will be useful whenever you require the alternating magnetic field, AC magnetic field, and it consisting of low coercive force, low magnetization, low retentivity. These three terms already we have covered: coercivity, magnetization, retentivity, right? So for hard magnetic materials, the hysteresis loop may be wider compared to the soft magnetic materials, right? And in this hard magnetic material, retentivity, coercivity, saturation will be the more compared to the soft magnetic materials. So till now what we have discussed, that I have mentioned in this slide. Smaller hysteresis loop area symbolizes the less hysteresis losses. So from the BH graph, residual magnetism can be determined. Thus choosing of the material for electromagnet is easy. If you want to prepare a electromagnet, so which material we need to consider, that will depends upon the residual magnetism that we may derive from the BH graph. So magnetic materials having a wider hysteresis loop may be used in magnetic tape, hard disk, credit cards, audio recordings, as its memory is not easily erased, right? So narrow means soft, solenoids, transformers, relays, so minimum energy dissipation. Clear? Applications. So one more is eddy current losses. Till now we have focused on hysteresis losses. Now we need to discuss about the eddy current losses. So actually what are the eddy current losses? Suppose if you are suppose we are applying an alternating magnetic field to a magnetic material. So what happened? We know that as per the Faraday's law, whenever the change in flux link in with the conductor, which may be magnetic material, then EMF will be induced. So what happened here? Whenever we are applying an alternating magnetic field or alternating supply to a magnetic material, then EMF will be induced in the material itself, and that material is conducting. If suppose magnetic material means it's conducting, right? So in that material we are developing EMF, and that material is conducting means that EMF may circulate the current within the body of that material, right? These circulating currents are called as eddy currents. These circulating currents are said to be eddy currents. They may be present whenever we are applying change in magnetic field only. And if you want to measure these eddy current losses, the formula is I square into R. And these eddy currents are not responsible for doing any useful work. Okay, so in the material, whatever the power is going to be wasted because of applied alternating magnetic field to the magnetic material, so these losses are said to be eddy current losses. And if you want to measure, the general formula is, I will give the formula for eddy current losses just to focus. So these hysteresis and eddy current losses both combinedly said to be iron losses or core losses or magnetic losses. Okay, so iron core magnetic losses, nothing but the sum of the hysteresis and eddy current losses. Clear? So just observe point wise. If the core is made up of solid iron of large cross-sectional area, the magnitude of the current will be the very large. Obviously, if the area is more means current will be the more. Hence, if the current is more, so whatever the losses will be high. To reduce the eddy current losses, whatever the methods we are having. Till now I said that eddy current losses generally I square R, right? So for the solenoid for large cross-sectional area, the current magnitude may be the high, then the losses may be high. So how to reduce those losses? So the magnitude of the current can be reduced. How to reduce the magnitude of the current? by splitting the solid core into thin sheets called laminations in the plane parallel to the magnetic field. Again, each lamination is insulated from each other by a thin layer of the coating of varnish or the oxide film. By laminating the core, the area of the each section is reduced, hence the induced EMF also reduced. So how the area is going to be reducing means the resistance. Simply we are increasing the resistance of that material, right? Simply you are splitting the soil, you are splitting the solid core. Simply you are splitting the solid core into thin sheets. One bigger part you are cutting into the smaller pieces, and again for that pieces you are providing some laminations, some jointing mechanism laminations. You are providing laminations means you are increasing the resistance of that material. So obviously the current may be reduces. So in this way we can reduce the eddy current losses. And one more method is by using a magnetic material having the higher value of the resistivity, like silicon strip. The material, whichever the material may consisting of higher value of the resistivity, you consider that by using, you design the magnetic material, then by design a magnet, if you will consider high resistivity material, then obviously the eddy current losses may be reduced. How to determine the eddy current losses? For the hysteresis losses, Bm power 1.6 Fv. So whatever the eddy current losses, Ke, coefficient of eddy current, and Bm square, F square, T square, and V. So what is the T here? We are providing laminations now. So what is the thickness of the laminations in meters? And F is frequency, V is the volume, B is the flux density, everything is know that. And these losses also measured in watts. Discuss about the go through that. So next concept is production of the induced force on a wire. Production of the induced force on a wire. So the effect of the magnetic field on its surrounding is that it induces a forces on a current carrying wire within the field. Whenever you will place a current carrying conductor in the magnetic field, whenever you will place a current carrying conductor in the magnetic field, then it may produces or it may induces a force, mechanical force. That force induced on the conductor is given by I into L cross B, the cross product of length of the wire and the magnetic flux density B. You need to remember I into L cross B, I into L cross B. So if you observe on the right side of the slide, Fleming's right hand rule, Fleming's right hand rule, Fleming's right hand rule, which is applicable for the generator if you want to identify the EMF direction or the motion of the generator. So for the Fleming's right hand rule, we need to consider only three fingers. First one is thumb, and second one is forefinger, and third one is middle finger or the center finger. So out of these three fingers, thumb will point, always thumb will indicates the motion of the conductor, and your forefinger will point the magnetic field, which is nothing but flux direction, always from north pole to south pole, and the center finger will indicate the induced current direction. Okay, so whatever the conductor, just you apply the Fleming's right hand rule and get the motion of the conductor if you know the flux direction or the current direction. Clear? So just remember this formula. F is equals to I into cross product of length of the wire and the magnetic flux density. Okay, so cross product is nothing but LB sin theta. So the magnitude of the force given by ILB sin theta. So if you observe here, the direction of the force is given by right hand rule. How to find the direction means with the help of Fleming's right hand rule. So if the index finger of the right hand points in the direction of the vector I, okay, vector I, current vector, and the middle finger points in the direction of flux density, just now I told, okay, just go through that. So induced voltage on a conductor moving in a magnetic field. If suppose a conductor is moving in a magnetic field, what about our previous case? If a current carrying conductor placed in a magnetic field, it is not moving. But now, if a conductor moving in a magnetic field, if a conductor moving in a magnetic field, Okay, if a conductor moving in a magnetic field, then a EMF will be induced. If a conductor moving in a magnetic field, then the EMF will be induced. That induced EMF is product of, okay, L and the cross product of velocity and the magnetic flux density. V is the velocity. Your conductor may move with a certain velocity. Okay, so cross product of V and B into L, and the product of L. L is nothing but active length of the conductor. The portion of the conductor, how much portion of the conductor is lying under the magnetic field, which is nothing but L, right? So the vector L points along the direction of the wire towards the end, making the smallest angle with respect to the vector V cross B. The voltage in the wire will be built up so that positive end is in the direction of the vector V cross B. Okay, these are the 2 points. Okay, so just remember this: induced EMF V cross B into L and force I into L cross B are sin theta. So how the force will be induced and when the EMF will be induced, that you need to focus. Okay, so when you are placing the current carrying conductor in the field, magnetic field, force will be induced and the formula is I into B cross L or else I into BL sin theta. So whenever you are placing the moving conductor in the magnetic field, EMF will be induced, right? V cross B into L. Clear? I hope you understand. Thank you so much.